the whole motivation here is if I can do all this stuff, I can take integrals, I can take derivatives, I can do all this stuff with power series representations. Right now we only know freaking 1 over 1 minus x. Is there a way to figure out like sine of x? What does sine of x look like? Sines suck sometimes. I would rather work with a polynomial. Screw sine. I want the polynomial that I can work with. Is there a way to get that? You know? Or a square root, or whatever function you can imagine. Is there a way to write a power series that would be just as good as that function for certain values of x? Yes, thank God, right? You're all like, I mean, no, there isn't. If you figure it out, let me know. So that's the whole point of 1110. So I kind of want to get into 1110 today, obviously. And we have today and we have Thursday to really focus on 1110. Because, like I said earlier, and some of you guys certainly heard about this coming into this class, I'm sure. Good God, those Taylor things. Oh, whoever Taylor is, we should go back in time and shoot him in the head. I've heard terrible things about Taylor. And McLaurin, for that matter. But these things are stupid freaking cool. So a power series, here's another way to kind of get to the point a little quicker. Well, let me write it more in general. Come on, Jeff. Right, this is just basically writing this here out. Cool. So that is a power series representation of some function. So that by itself is a power series. That by itself has merit. But now we've tied it to being representations of functions. We saw from section 11.9 all this shit you can do if you know the power series representation for a function. So 11.10 says, well, what about all those other damn functions we've learned? Is there a way to represent those as power series? Because then we can do all this stuff to them. So what we're going to do real quick, I want you to see why it makes sense. And then it's such a recipe method of finding Taylor polynomials, finding what these have to be for this to work. It's such a recipe-ish method. It's really, you can't beat it. Truly, you can't. So here's what's got to happen. So let's say this A is where I want to create my my series. I want to create it so that it's good for things close to A. That's the idea, right? If I go to infinity, this series would be good for that function for any value of x that works. If I stop somewhere, like if I stop here, the idea is the closer my input is to A, the better it works, right? So I have those two kind of things going. If I go to infinity, this thing works for any x that's in my interval of convergence. Do I want to go to infinity all the time? Hell no. So depending on what number I'm kind of working around all the time, that's what I can build this thing up around. So for values of x that are close to A, this thing is going to work really well. Obviously, at A, it's going to be perfect. Because what's f of A, for example? What happens f of A? I get C0 plus 0 forever, right? So f of A is this constant. So what I really want you to realize what that means is as I build this, all these other things are going to be related to derivatives, I'm going to find here in a minute. But if I build this for a function and then I plug an A in, I only have to go out to this term to be perfect. I can stop at one term. The minute I get a little bit away from A, I've got to go a few more terms out to make the approximation better. If I get really far away from A, I've got to go way the hell out in my series to help for being so far away from that perfect spot. How the hell, I gave it away just a second ago, how do I figure out these other constants? Because remember these constants, what's the point being made here? Cn. What does that mean about those constants? They might be what? Dependent on n. So it could be like, we've already seen one earlier where it was sum of n x to the n minus 1, so the constants were all n. So constants were 1, 2, 3. Right? So they could be any function of n. So really what I'm doing now is I'm trying to figure out what are these constants, what do they have to be in terms of this function so that I get a series that models that function. Are you guys kind of with me here a little bit? Not really yet. Okay, sorry. So here's the theory, and then we're going to attack a function that we already know and show you what it looks like as a series, and then verify it by plugging some stuff in, right? Who has an idea? So now I know that CO is whatever f of a is. Whatever the function evaluated at that thing is, that's what the first constant is. So a quick side note then, remember this was this? What's a in this one? What's a? 0. At 0, what's the function? Well, at 0, what's the function? What's the value? 1 over 1 minus 0 is 1. And sure enough, there it is. That's the value of the function at the point that I've built this thing around. Right? Just a quick little simple example of how that's going to work. How in the world do I get these other constants then? That one was freaking easy as hell because the minute I put a in, everything else died. How can I make something like that happen again for me?
If x minus a equals 1 or something.
See, I need to have the same inputs, don't I? So it's always got to be an input of a. But you're allowed to do things to your functions. For example, I'm going to give it away. I already gave it away earlier, but what's f prime of x? So I know this. What's f prime of x? 0. That's a constant, right? Move here. What's the derivative of this?
1.
C1.
C1. Right? You guys cool? So it's C1 times 1. I agree with you. So it's C1 plus 2C2 x minus a plus 3C3 x minus a squared. Forever, right? So now notice what I've done. This happens a lot in math too, where I just shift things over. Now what's f prime of a? F prime of a must equal C1. Let's do one more iteration of this, and then I'll show you the general idea. So, who's got an idea? What do I do next? Take another prime, yeah? F double prime of x. That dies, so I get, this is 0. 2C2. 633 x minus a plus blah blah blah. So f double prime of a must equal 2C2. So C2 must equal f double prime of a over 2. What would C3 be? You can kind of see it coming up. C3 would be f triple prime of a over 6. Does anyone see the pattern now? What's it going to be? There's 1 over 2 over 6. If I did another one, x to the 4th would be, if I go up here, so that would have been plus 4, C4. This would have been plus 12, C4, x minus a, which would be 24, C4. So I'm going to eventually divide by 24. What is that becoming related to? 1, 2, 6, 24. I keep multiplying by the next number, so it's a factorial, right? 1 times 2 is 2, times 3 is 6, times 4 is 24. So what's the general Cn going to be then? So we did enough to kind of get the pattern, and the book's got this basically in there too, I think. Page 734, they kind of do what I'm doing. What's the general pattern going to be? Cn So I've got my f of x, sum of Cn, x minus a to the n. If I can figure out what these are, I've got my whole series. Cn has got to be f
N.
over
N factorial.
n factorial, right? That's what Cn has to be. So what is the Taylor series? This is called a Taylor series. Taylor series for some given function f of x. It would be f, well, let's see, how do I want to write this? Yeah, f of a plus f prime of a over 1 factorial. This is really over 0 factorial, truly, but let's let that go. Plus f double prime of a over 2 factorial, right? And what am I missing in here? Those are my constants. I need my little x minus a squared. Got too focused on the constants. Do you guys see how that's just this written fully out with the CNs in there now? I know what the CNs are. I know what the constants have to be so that all the derivatives match up. So I just throw them into the formula. So let's do an example with a function. What function you guys want to use? A trig function or a... Let's do sine. Sine is a good one to do, right? Sure. All right. So let me show you the way to hit this then. The first thing I do is I make a list of what my constants are going to be. And I know how to build my constants now. They're all based on the derivatives at some value. What do you want to expand this around? What angle? I mean, do you want it to be near 90 degrees? Do you want it to be near 0 degrees? Let's do 0. Let's start with 0. Cool. So let's say around a equals 0. So that's the kind of language I'm going to say. I'm going to say we're building this thing around a equals 0. So it's going to work really well the closer to 0 my inputs are. It'll work for every x in the interval convergence if I go out to infinity. But if I stop somewhere, I better be close to 0 so that it works, so the approximation's better. Right? If I stop too early, it's only going to be approximation. So the first thing I do is I start to make this list. F of x is sine of x. What's f prime? Cosine. F double prime?
Negative sine.
Negative sine. Let's go out to 4. F triple prime and F 4 sine. So what's f of 0? 0. Sine likes y, 0 is all x. What's f prime of 0? 1. F double prime is 0. F triple prime is 0. F. Okay, so that's all we need for the pattern, right? So I always try to do a few and see if there's a pattern I can see developing. And you can pretty much see the pattern there. Right? Keeps bouncing around the unit circle, right? So now we piece this thing together. So my f of x is going to be approximated with the series f of a plus, well, let's just get to the point, f of 0 plus f prime of 0 over 1 factorial x plus double prime of 0, 2 factorial x squared, and so forth. No, Jeff. Now, personally, that is actually relatively easy to remember. Everything is related. The derivative I take, so the zeroth derivative, so it's over 0 factorial, and there are 0 x's. First derivative is over 1 factorial, there's 1 x. Second derivative, over 2 factorial, there's 2 x's. I mean, that's silly. I wish to God everything was that easy to see the pattern for math.